Should we go on?
Yeah, I think we should.
Okay.
I need your microphone. Okay, well, welcome everybody, and thanks for coming. I know most of you. For those of you who don't know me, I don't know you obviously. My name is Danny Dilks, and I'm a postdoc with Nancy Canwisher. And one of the things that I am interested in is face recognition, and in particular, the development of face recognition. So as Nancy has nicely shown us, that in the adult, there is clearly a dedicated piece of the brain that's responsible for face recognition. And she called this in 1997 the fusiform face area, the FFA. And again, just to revisit that for a moment, what that is it's a piece of cortex, again, that is going to preferentially respond to many different sorts of faces and not respond, or not as strongly respond to some non-preferred categories like objects and bodies and so on. Now, the project that I'm involved in currently, however, is not looking at the FFA in the adult, but rather looking at it in the child. So what are we learning from scanning your children about the development of face recognition? And we can do that by looking then at the FFA, the precise piece of tissue that we know exists in the adult. How does it change over development? When does it arise? And how does it look like an adult, and when? So the research question clearly is then, when does this FFA develop in childhood? And before answering this question, FFA, like I said before, is clearly a dedicated piece of tissue in the brain, and I've got to be able to scan your kids. And so there's a much bigger challenge in this question, and that is just simply, how in the world am I going to scan your kids? Your 5- and 6-year-olds in particular. This is the youngest I've gone thus far. I've done one 3.5, and it's pretty successful, but not nearly as successful as the 5 and 6. But how in the world am I going to do that? So half of this talk is just going to be telling you how we did this, and then trying to show you some really beautiful preliminary data and give you a feel for what we are learning about the development of face recognition. Okay, now, there are a couple of challenges in precisely this. How in the world am I going to do that? And the first thing is that when you're in this scanner, it is crucial for one to lie still for an adult's typically 2 hours, so you accumulate enough data, because Nancy had shown you that time course and they're extremely noisy. So I want to get enough data in a child, and the child we figured was able to stay in there for 1 hour at most. So we really are trying to get the child in there for 1 hour and to lie absolutely still. There. Lie absolutely still. Your parents, you know this is nearly impossible, I think. Okay? Now, the next thing is often when we tell the child to lie absolutely still, and you'll see how we do this, one way is to say, act like a statue. When you ask a child to act like a statue, they stiffen up like this, right? And they're very tense, and there's some movement, and we don't want movement in the scanner at the same time, so we ask the child to relax. Again, your parents, and you know that this is probably not so easy. And the third, probably most difficult, is to have this kid in that scanner for 1 hour while being relaxed and paying attention. Now, how in the world did we do this? So we believe we met the challenges, and I'll show you data to prove that we've met these challenges in the following way. So the first thing that we had done is Ellen, and I think you all know Ellen quite well, made this gorgeous book that she sends home prior to the visit. And in this book, she introduces the child to us. She shows the child pictures of the scanner, so the child's not scared when he or she comes and looks and sees this massive machine. And then we have these 3 S's, these 3 words that begin with S. And these 3 words actually help us overcome the challenges that I talked about before. And those 3 words are still, soft, and super duper. Still, obviously, tells the child to not move, to lie in that scanner for 1 hour. Soft is for them to relax. So we don't want this to be an unpleasant experience for the child. We want it to be very, very pleasurable, and we want he or she to stay in the scanner. So we want the child to relax. And super duper means that they need to do a super duper job. So this is they're going to be paying attention. So these words are taught to them in this book. When they come here to visit us, I go over these words over and over and over and over with the child, so they get the 3 S's, and we cross our fingers at that point. Okay, now, the second thing we do is upon the child's arrival, he or she is first introduced to scanning in a mock scanner. So he doesn't first see the real scanner. He sees a pretend scanner, which is also actually pictured in the book. And the pretend scanner looks something like this, which looks very much like the real scanner. It's just slightly smaller. But the child is asked to lie on the bed, and he or she's going to go inside the scanner, watch his or her favorite movie. And there's also noise pumped into this real scanner to mimic the mock scanner, to mimic the noise of the real scanner. So we're trying to just make the environment nearly identical to that of the real scanner, so there's no surprises once that child is in the real scanner. And to give you just a closer picture here, here's a little child in here, and he's watching his movie. Here's the mirror. It's back projected on that mirror. Now, how in the world do we get these kids to stay still? Here's how. If you see this little plastic arm here, there's a camera attached to that. And you see a little sticker on this little boy's head here. This is a motion detection camera. If that head moves, that means the sticker goes out of the frame of the camera, and his favorite movie shuts off. It's incredibly effective. Try it at home. Yep. Okay, so at any rate, it takes only about 10 to 20 minutes of this so-called training for this child to realize what it means to literally stay the first S word still. Okay, now, Nancy had alluded to this next. So we've now got them still. We need them to stay in there and pay lots of attention. And the way that we're going to do this is by presenting them some engaging stimuli. And these are movies that Rebecca and the cinematographer Anna Wexler had made for us. And let me just show you what we call this dynamic localizer and why we think it's more engaging, not only for children, but for adults as well. So they see close-up pictures of faces. And recall, I'm interested in the face recognition system. So showing faces obviously is crucial. We have body parts as well. Nancy had talked about there being a body region. We have objects, toys in particular. We have scenes. Nancy had also talked about this place area. And then finally, these weird-looking scrambled things. And the kids like this, but they're actually used as contrasts. And I can describe to you what that means later on. OK, now, the child, well, he or she is in the scanner or watching these movies. And the real scanner looks like this. So it doesn't look terribly different than the mock scanner. So the child, again, is not afraid to go into the magnet. And here is one going in and one coming out. And look how pleasant he looks. Doesn't he look pleasant? Right there. OK, now, and the last point then, the way that we met these challenges, scanning your children for 1 hour, is we designed this new fancy coil made just for your children, made for children 5 and 6 years old. We now have another one made for children 7 and 8, and so on. And let me just show you a picture of that and tell you why it's important. Okay, so what we have here is the head coil. So this is where we actually are getting the signal from the brain, of course. That's inside the scanner. You actually saw the child inside that with the mirror from which he or she watches the movie. This was a model of, I think, an average of 100 kids between 5 and 6. So that's the average head size. And you can see that the people that made this coil molded it perfectly to fit the child's head. So this does a number of things and why it's important here. At first, the closer you can imagine, the closer the coil is to the head, the better signal you're getting. So that's just from a data perspective. This is wonderful. However, what it also does, it fits so snugly and so nicely and so perfectly in your child's head that he or she they really can't move a whole lot. And this is perfect for having them lie still. Yeah? So it's very comfortable nonetheless. OK, now, the kids love it. They really do. And it's really a pleasure to work with your kids. And let me just give you, I couldn't resist putting this in here. This is a phone call that we got from a child who wanted to participate in this study but wasn't able to. Many of you actually, I've scanned one of your children and maybe another one has been here, and they say, I want to do this, and then we call them back. So there's lots of excitement even in the children that can't go in. Of course, Sean, right? So here's just some of the excitement, yeah?
I'm sorry, but I live in the UK. Is there any way that I could help? Because, and get involved because I live in the UK. No way I can, but I really want to. Thank you. Please can you get involved? Thank you. Bye-bye.
They love it, right? Okay, so this was a phone call that Ellen had gotten from this little child in the UK. I think she was actually at the museum and heard about this study, and at the MIT museum, heard about the study. When she went home, she then made this call, hoping that perhaps we'll fly her over something, and we just might, I don't know. Okay, but at any rate, the kids really enjoy this, and it's really a nice experience for them. So now that we've met these challenges and we're able to scan children as young as 5 years old, let me just show you some preliminary data and return back to our research question is, again, Nancy talked about us having, the adults having this FFA, and what we don't know is precisely when that FFA develops in childhood. Okay, now, the way that I've done that thus far, or attempted to answer this question thus far, is I compared the FFA in children, yours, to adults on two measurements. You can ask one about literally the size of that neural tissue, that dedicated piece of cortex, and you can also ask about its selectivity. How much is it going to respond to faces? And you might think then, using these two variables, you might have a number of hypotheses. And the first is literally that FFA gets bigger over time with age and experience. So Nancy had said something about this hypothesis. Maybe selectivity or size has to do with the number of people you know, the number of faces literally one sees, right? It's maybe along those same lines, but as we get older and we experience faces more, maybe this tissue grows. Okay, another hypothesis is that maybe this area gets more selective with age and experience. So almost like a fine-tuning kind of argument, right, which is certainly possible. And then finally, maybe the FFA is in fact the same as it is in the adult. There is the genetic evidence that Nancy had shown us to suggest certainly that maybe this is something that's hardwired, and maybe it's hardwired and looks like an adult very early on. Okay? So these are the three hypotheses for which I'm trying to tear apart. And the way that I'm doing that thus far is I've looked at 8 children in particular and 8 adults while they watched our movie, the movie that you had seen, 4 times. And this is an incredible amount of data to actually get on a young child. Okay, now, before we ask whether it looks like an adult, we better find out whether this 5- and 6-year-olds even have one. And I can tell you that, in fact, all 8 children that I've scanned thus far exhibit a clear FFA. And I don't only just have to assert that or tell you that, I'm going to give you some examples of that. So we have here let me show you first how it looks in an adult. So as expected, like Nancy had shown us, here is in one adult, and we can see the right. So in my data, the hemispheres are flipped as well. Yeah? So you see here a beautiful FFA, exactly what it looked like in Nancy's data. A beautiful FFA in the right hemisphere, and one a little more puny in the left, but this is typical as well, and one adult. And in the second adult of the 8, of course, we see also right and left FFA. Very nice. Again, not or absolutely expected. Okay, so what is going to happen in a 5- and 6-year-old child? Well, what happens, like I told you before, is they all exhibit it. And here you see a very nice, clear FFA in this child, and this child happens to be 5.5 years old. In the left, a puny one in the right, and another example, another child, again, with the left and right FFAs. Okay, so now they have it. And now we can go on and we can ask, well, how does it compare then to yours in size and selectivity? And with respect to size, these are just example brains. This is not the size of this particular person is what I'm going to give you. I'm going to give you an average number. So one thing that we can do with respect to size is these images. You can imagine like 3D pixels. That's what these images are made up, and these are called voxels. So you can go within that particular region and literally count how many voxels are in it, and that's going to give you a measurement of size, or at least one measurement of size. Now, in the adult, in the right FFA, on average, over these 8 people, they have 18 voxels within this region. And in the child, they have 29 voxels. So it's certainly not getting bigger over time. In the left hemisphere, in the left FFA, the adult has approximately 17 voxels on average and 19. And I can tell you that when you do the appropriate statistics on this, there are no significant differences between the size of the right FFAs and the size of the left FFAs between children and adults. Okay? So to the size then, like I said before, kids seem to look just like adults with respect to the size of the FFA, or number of voxels. Okay. Now, another variable we can look at is selectivity. And again, this is how well this area is responding to faces. We know in the adult, it responds incredibly strongly to faces and not so much to other categories, nearly 2 times to faces than it does to others. How about in children? So how does the FFA respond to these different movies that I had shown them, these different categories? Well, let's take a look first in that right FFA again, the one that we typically were talking about, Nancy was typically talking about, and these are our 8 adults. On the x-axis, we've got the different movies, faces, bodies, scenes, objects scrambled, and we have here, this is something called percent signal change. That's how much more it's responding to that category greater than that fixation, the baseline, like Nancy was talking about, the dot. Okay? And what you can see while you're looking at the red bar is that in the right fusiform face area, in adults, it responds significantly more to faces than it does to any of the other categories. This is the very, very typical pattern. Now, how about children? What is going on? How selective, or how is their FFA going to respond? And you can see that it responds nearly identically to that of the adults, in that it's significantly greater response to faces than any other object category. Now, there's the beauty of the brain that there's 2 hemispheres, so we can not only look in the right FFA, but what goes on in the left FFA. And you can see that it's the exact same pattern. So the response in the left FFA in children, again, is certainly responding more to faces than any other category and looks nearly identical to that of adults. So in terms of the response profile, or at least this one way of measuring the selectivity, it looks as though children and adults are the same. Okay, so I'm going to end very shortly, and then Rebecca will come up here. But let's return to the hypotheses then, at least that we were trying to tear apart. The first is that the FFA gets bigger with age, and I'd shown you that that is not the case. In fact, if anything, there might be a trend that the FFA, at least in the right FFA in a child, is slightly bigger. This is a trend. There's not a significant difference there. But it's certainly not bigger. The second thing, I showed you data that the FFA certainly isn't more selective in the adult than it is in child. In fact, they look very, very similar. And so it leaves us with then those data being consistent with the FFA being very similar in the adult as it is in the child. Okay. So I started the talk with asking the question, what are we learning about the development of face recognition? And what I can tell you thus far is that the FFA develops early. So this is 5 or 6 years old, and is adult, in fact, in size and selectivity by at least 5 years of age. Now, this is not only important information for normal development, but it's also critically important when we're going to look at populations, atypical populations, developmental disorders, for example. And this is actually part of a much larger project. And these normal data will be part of a much larger project where we are going to look at children, for example, with autism. So there are some theories bounced around out there suggesting there might be some face processing difficulties in autism. Well, this is a perfect way to look at that, right? We can now look at what the FFA looks in how these FFA looks in people with autism. So that's something that we're going to look at, of course, next. And then finally, Nancy also talked about all of these other these very specific regions of cortex, like the PPA and the EBA. And you saw the movie had all of these stimuli classes. I can now look at those and ask exactly the same question I asked in the FFA. What do these look like over development as well? And stay tuned. Come back next year, 6 months, whatever, and I shall give you that answer. I thank you so much. This would have never, ever happened without you and your children. So thank you.
I noticed in the chart the one thing that seemed, and again it didn't seem significantly, but it was the objects. The scrambled object seemed to be the one thing that stood out a little in the children. Do you think that's significant in any way?
I'm not sure. I don't remember either.
In the
Let's take a
right
look.
FFA, the scrambled objects were slightly higher than 0 in the kids.
I think they were 0
Zero
in the
in the
human,
adults.
in the
Yeah, I
adults.
saw that.
Good eye. I don't think it's significant. I don't remember exactly. I don't think it's significant.
Because I mean, that kind of ties with what you say about the selectivity. Because it could be that the children are looking for patterns that we've decided now. And are they looking for a face in that object pattern?
Yeah, it's certainly possible. Yeah. Yes.
Are the voxels the same size in adults and children? I mean, is that region the same, or does it grow with age, or I mean, relative to the brain size? Is that relative?
So they're the same size right now. So the voxels that I use, the size voxels in children and adults, is exactly the same.
Okay.
So that's an answer to that question. And then the second, in terms of if something's growing, I'm showing that there's no difference. So the child's brain, you might imagine, is smaller, and it is smaller.
It is smaller.
Right? And if then you had to normalize to that, right?
Yeah.
You would only need to do that if you found some sort of difference straight away. And if you're finding no difference, then the normalization isn't going to do it.
Right.
Although, given that we have a bit of a trend that the face area is a little bit larger in the kids and the adults, if we normalize, that might be significant.
It might be much larger.
Much larger. Yeah. Well, the answer actually
Your
is
face area is
no,
getting
it's not.
smaller every day.
Yes, even after normalization, they're still not significantly different.
Okay.
Even that trend.
Yeah.
Do you have any data that shows when the FFA actually starts to develop?
Oh, we'd love to know, because this is a problem, because, it's hard to scan kids younger than 5.
Yeah.
I'm actually guessing it's there way early, a year, 6 months, I don't know, I mean, but that's tough.
If you have any 6-month-old babies, we're taking all donations.